Okay, so how about this here? We got L feet. I'm not even telling you how much. L feet of wire is used to form the perimeter of a square and a triangle. What fraction of the wire should be used for each figure in order to maximize total area? So everybody see what's going on there? We got this piece of wire. We're going to cut it into two pieces and then bend it into the shape of a triangle and a square in such a way that we can maximize total area. Okay? All right, so I guess for our picture, I mean, I can draw the wire, I guess. That's kind of boring. Here's the wire. That's length L. But probably more importantly, we're going to break that up into that and an equilateral triangle, we'll say. Okay. All right, so what do I do? Okay, so I need to come up with a primary equation, right? Okay. What's the area of the square? X squared. Okay. So we'll say we're going to call. That's fine. We can call the length of wire for the square. You know, for a side of the square, we can call X. That's good. So then total area is going to equal X squared plus. What about this one? 1/2 base times height. Actually, for an equilateral triangle, if we call this Y. For an equilateral triangle, we have a little formula. It's nice to know. You don't have to, in that one case, because it's a regular polygon, you can write it in terms of the side length only. You don't need the base and the height. The formula is square root of 3/4 times side length squared, which in this case is Y. Okay? Yeah. I just said it was. I forgot to write it up there. But we'll make. I'm saying it's equal. I'm telling you, I want it to be equal. That'll make life a little easier for us. That's true. That's true. So then, what's the problem with our primary equation? Two variables. So we need an equation of constraint. Now keep in mind that the equation of constraint, the secondary equation, has to come from the constraint. What's the constraining part of this problem? Why isn't the area infinite? Yeah, I have a length of wire that's fixed, right? Okay, good. So the sums of the perimeters must be L. Sure. Okay. So our secondary equation then, must be 4x plus 3y equals L. Okay. It doesn't really matter which one we solve for. Just solve for y. It doesn't make any difference. If I solve for y, then what am I going to get?
From both sides of X and there's 3 sides of Y.
Yeah.
And you're using up.
So you cut the thing in two different wire in
Yep.
different pieces.
Cut it in two different pieces.
Oh, okay. I thought you were doing the same wire.
Y L minus. Well, I can, but if y is the length of one side of this, then I need 3y to get the whole perimeter.
Yeah. What if you use extra?
But how do I know? Then I'm making an assumption that's not founded. I don't know that those are the same.
No, I'm not saying they're the same. I'm saying L minus 4y would be how much y would be.
You're right. You're right. Exactly. But then I'm going to have to divide that by 3 to get y anyway, and that's what I'm doing right there. That's what we just did. When we solve for y, look what we do. We end up getting L minus 4x divided by 3, right? Okay, so there's our substitution equation. So we'll push that up to there, right? And then let's see, what do we get if we do that? So now we're going to end up eliminating the y because that's the variable we're substituting, right? And so we get area as a function of x equals x squared plus the square root of 3/4 times that quantity squared, right? So that's going to give me, well, we'll just write that. Minus 4x over 3 squared. Okay, and then why not pull that 3 squared out? So we've got A of x equals x squared plus square root of 3 over 36 times the quantity L minus 4x squared. Okay, so there's our primary equation. Good. So now if we let's follow our recipe for this then. So step 1 was define the variables, draw our picture. Got it. Step 2 was the primary equation. Did that. Step 3 was, we needed it this time. It's optional, but we needed it here because that was the secondary equation. We had to eliminate a variable. And then step 3 ends up right here. We've got our primary equation in terms of a single variable. Now what's left?
Two variables though?
How are there two? No, is L a variable?
Do we have a value for it?
No, we don't, but it's fixed. Yeah, I'm glad you brought that up. L is what we call a parameter or a constant because it's, sure, we could say when we're all done, our formula is going to be written in terms of L, but it's not a variable because it can't vary during the problem. Now, X and Y can. For a fixed length of wire, depending on where I cut that, I could make the square bigger and the triangle smaller or vice versa. Those are quantities that can vary within the problem, right? But L can't. This problem wouldn't make any sense if the length of wire were changing, then we couldn't do the problem. It's got to be a piece of wire of a certain length that we just haven't pinned down. Okay? So that is a constant. The only variable we have is X then. Okay? So we can do the calculus, but before we do the calculus, we don't want to waste time on the calculus. We want to only have to analyze the function where necessary. So we want to find the domain of the function first, and then we can ignore any critical numbers or any weirdness that happens outside of that domain. And a lot of times that's really handy to be able to ignore. Yeah.
What do you have in 36?
Because when I squared this out, 3 squared is 9, and so I just pulled that out into the constant.
Oh, shucks.
Okay?
Shucks.
So now, how about the domain? With the domain, we want to look at, sure, we can look at this mathematically, but mathematically there really are no restrictions on x, are there? I mean, the x appears in the numerator. It's not inside a radical. So mathematically, x could be anything. But if we look back at our picture, that's a good place to go. What's the biggest that x could be? What are the extreme cases for our problem?
X has to be solved.
Okay, for one extreme case would be the whole length of wire were used entirely for the square, right? The square were as big as possible. In which case, y would be 0. Whoops, y would be 0, and 4x would equal L, right? And so the biggest x would be L over 4. Right, so there's the maximum. There's the upper end of the limit. What's the smallest that x could be? 0, right? Because it could all be triangle. I could use the whole thing for triangle also, right? So our domain then, in this case, we're able to get to just by looking at the wire. The domain is just 0 to, what was it, L over 4. And I want the squared brackets there, don't I? Because those are endpoints that we have to consider. I mean, they're realistic possibilities. Okay. Make sense? So now we can just do calculus, right? We've got this thing written in terms of single variable. Now we'll just differentiate and we'll make a chart, you know, and figure out, we want to figure out where the maximum is on our domain. So let's do the calculus. In fact, let's probably go to the next page. Wherever that right. Okay, so A prime. What do we get from the first term?
2x.
2x. Plus, let's just, what about that guy? You tell me, what should we do with that? I mean, maybe that's a dumb question, you know, maybe I shouldn't even brought it up. What do you naturally do with that number that's out in front? Just leave it there, right? So all the action is going to be, here's the part that involves a variable. So when we differentiate this then, we differentiate by the chain rule, the derivative of something squared is
To something.
2 something. So that when the 2 comes out front, we can reduce that to the square root of 3 over 18, right? 2 over 36 times something to the 1 times,
I 3 over 18, I got it. You skipped the step.
And
Well,
three
you
or
took
four.
out.
yeah, if I bring the 2 out front, then I get 2 over 36, which is 1 over 18. Right. Okay, we good with that? Okay, and then what about the last step of that chain, the last link in the chain? Derivative of negative 4x, which would be,
-4.
what's the derivative of L?
1.
No, 0. How come?
It doesn't change.
Because it's constant. Good. Okay. And I guess we could even reduce that a little bit more, because 4 over 18 would reduce to 2 over 9, so we get a prime of x equals 2x minus the square root of 3 over 9 times L minus 4x. Okay. What's that? The 2, oh, 2, sorry. You're right.
Yeah.
The thing you're watching. There we
Yeah,
go.
I was trying to think
Whoops.
of something. Maybe this is.
Sorry. No, I didn't. That was a bad trick there. That was a wrong trick. Okay, so there's our derivative. We can come back and take a second derivative if we want to. We don't have to yet. So let's find the critical numbers, though. Any place where the first derivative could be undefined.
I don't think so.
Okay, and why? You're correct.
There's no variable on denominator.
Okay, no, x never shows up in the denominator. It's not in a radical anywhere of any kind, so we're fine. So we just want to find the 0 of that, though, right? 0 of our first derivative. So how do you propose we do that? It's not a big deal, really. What we're doing, x is linear here, isn't it? So we're really just solving a linear equation for x. We don't have to do anything fancy here, but what is the algebra we go through? Okay, we got to isolate the variable. In order to do that, why don't we distribute this constant so we get 3 terms, then we'll pull all the x terms to one side, constants to the other side, factor out the x and isolate it, right? So 2x minus square root of 2 times the square root of 3 over 9L plus, we're going to get 8 root 3 over 9x equals 0. Check me as I go. Is that right? Does that seem right? Okay, so we got the x's on this side. Let's push this term to the other side, right? And we get 2x plus 8 root 3 over 9x equals 2 root 3 over 9 times L. And we probably could have combined steps there. I would argue that we really could have probably, in hindsight, you'll tell me how we could have done this quicker. What are we doing over here on the left side? Okay, so factor out an x. Right, so we've got x times 2 plus 8 root 3 over 9 equals that. Right? Okay, and then just divide both sides by that. So we end up with x equals 2 square root of 3 over 9 divided by 2 plus 8 root 3 over 9 times L. Agreed?
Maybe it seemed like it's not that hard.
Well, it's not that. Once you you guys could do this. You really could. And the value, I think, is just if you know the steps like you do, this is where I think calculus, where you really kind of put the pieces together, is when you go through the process and see it work. Now, so this is going to end up, explain to me what this,
It's going to tell you how big L is.
yeah, it's going to tell you what fraction of L, isn't it?
Yeah.
Right? So what do you know about this red stuff here?
It's just a number.
It's a number. And what does that number, to be meaningful for us, what does that number probably need to be between? I mean, it needs to be in our domain, right? which was from 0 up to L over 4. And so why don't we, up to 1/4 L, right? 0 to 1/4 L. So this number, to be in our domain, would have to be between what? 0 and 1/4, right?
I don't think it is though.
Because there's our,
Oh, yeah,
Right.
it is, because it's 2 plus 1/4, which is 2 1/4, right?
let's just see. Put that in your calculator just to get it as a decimal and see if it makes sense. Someone is. Yeah.
Oh, okay, and then.
Do it, yeah, in the end.
We could clean that fraction up. There's no point. We just want to get an idea if it's in the middle or not.
0.1087.
So roughly 0.1087.
That's not for, I think, clean those.
So roughly 0.109 L. So that is on our domain, isn't it? That's between 0 and 0.25 L. So we got to know then if that's a maximum or a minimum. Now we got a choice. We can do the first derivative test or the second derivative test.
First.
Okay, naturally people would say the first because it avoids a little calculus, but if you look at this, second derivative is pretty easy. All we need to know is the sign of the second derivative, right? So let's grab this first derivative. I'll show you. I'll show you why you don't even really have to do it. You can just look at it and see what the answer is going to be, literally. You don't, really, it's not that bad.
You can't just plug that into that.
Well, you could. I mean, you could, well, if you plug it in there, it's going to get 0. Because we just found the 0 of the first derivative.
Why do we not know if it's a maximum?
Well, we don't know this time. We don't know this time because the endpoints aren't 0, right? They could be real values, and so we don't know. Hold that thought. Hold that thought.
I got it. I actually have it. I don't know.
Okay, now everybody, now focus. We got this far. You got to really see it. Yan, good question. A lot of times we know if it's going to be a maximum or a minimum because if you look back at some of the other problems we've done, we've had situations where on our domain we've known that the endpoints have been ridiculous. Like for example, when we did that one with the box we did in here, right? Cut the corners out. And if we looked at the extreme values of our domain, one extreme value was the box had no height, so it had 0 volume. The other extreme value was the box had no base, so it had no volume. If there were only one critical number on the domain then, it had to be a maximum, right? Doesn't that make sense? In that case, now I want you to see this. On that, in that particular case, if we knew that one endpoint was at 0 there and the other endpoint was at 0 up here, and there's one critical number in between, it can only have one peak or one valley then. Well, it has to be a peak because there has to be some volume for some box that we can create, obviously, right? So we know we're going to have some positive values here. So the one critical number had to be a maximum in that case, right? We could just reason through that without having to do any additional calculus. One critical number meant one maximum. But this time it doesn't. This time we've got our endpoints. This will be the red graph. Our endpoints are going to be, I don't know, maybe there and there, right? If it's all a square, we'll get one area. If it's all a triangle, we'll get the other area. But in between, is it doing that or is it doing that? It could be one or the other, right? We don't know. It could be a minimum or a maximum, couldn't it? So we gotta go look. We gotta see. Now, why would we want to do a second derivative? Well, because look, if I distribute this number through, wouldn't you agree that if I distribute that, I'm going to get a prime equals 2x minus some constant, call it C1, plus some other constant, call it C2 times x? I don't care what the constants are, because when I differentiate this, a double prime of x, that's going to go away, right? But aren't I going to get 2 plus some other positive number? I'm going to get a positive constant answer, right? So I know that the second derivative has to be positive valued. Just by looking at this. Everybody see that? Because if I distributed that number, negative times negative is positive, I know if I have a positive number times x, when I differentiate, I'm getting a positive constant result. So you could just say, what I would have said in college on this problem, I would have said, by inspection, the second derivative is positive. So we know that when we make our table, okay, let's put our domain in there. Our domain went from 0 up to L over 4. And we had one critical number in between. I don't even wonder, that critical number was ugly. Let's just call that critical number for now. I don't want to, I'm getting lazy. I don't want to write it all down. Let's just write it down as, where is it? It's that thing, right? Okay, so it's that times L. Here, I'll just do this. This is, I never thought it would be cheating. Let's go. Oh, that's good. I can do that. Yeah, that's better. 109. So our one critical number was roughly 0.109 L. Okay, that was a 0 of the first derivative. And what was the sign of the second derivative everywhere? Positive. So what is that? No. It's a minimum. It's happy. Second derivative is positive. It's a smiley face, right? So that's a minimum. So we know then that this thing is going to look like, if I were to graph it, we're in that room, I'm going to get that, the minimum, right? So I'm going to get extremes at the endpoints, right, and a minimum in between. So which of the endpoints is going to be extreme? I don't know. We have to go see. Yeah.
So positive, the second derivative is a goal, and then the negative is the I thought it was the other way around.
No, positive concavity means concave up. It's holding water. Negative concavity is concave down. So you can, and in the table, you always know that positive is happy, negative is sad. Okay.
What? More.
Yeah.
Okay, so if we go back then to our original, how about if we go back to here? Here's the area written as a function of x and y. So we could look at the two extremes, couldn't we? We could look at the extreme where x is 0, right? Or where x is L over 4, right? Or y is 0. So there's, right?
Yep.
Oh, there's area. Whoops, there's area. So we get, did we not ever write area? Oh, there it is in terms of x and y. Good. Okay, so if, where's the best way to do that? Well, we can do it here. That's fine. So if y is 0, then x is L over 4, right? Does that make sense? Let's do it here.
Oh, yeah.
Okay. If x is 0, how about that? If x is 0 here, then that stuff all goes away, and I just get square root of 3 over 4 times L over 3 quantity squared, right? That's a good place to do it. So we'll say A of 0 equals, that goes away, so that is what? Square root of 3L squared, square root of 3 over 36, L squared. Okay? There's the area if it's all triangle, right? If x is 0. Now, what if y is 0? Well, if y is 0, then that means that x is equal to, or excuse me,
Why?
If x is 0, sorry. If x is 0, then y equals L over 3, which we knew, right? And x is L over 4, so we could plug in L over 4 here. How about? That's how we do it. Area evaluated at all x, where it's L over 4, no y. Gives us what? Gives us L over 4 squared plus the square root of 3 over 36 times L minus 4 times L over 4 is what? Yeah, is L minus L, so that's 0, right?
It goes away.
So look, that whole term goes away, doesn't it? So I just get L over 4 squared, which is equal to L squared, or 1 over 16 L squared. So I get two possible answers. The square root of 3 over 36 L squared, or 1 over 16, which is bigger. Somebody.
We already said it once now.
1/16 is bigger, isn't it? Slightly bigger. Okay, so this is the winner then. The winner is if we're all the way over, so y is 0, L is its maximum, which is 1/4 of the, so it's a square. Okay. Now, we probably could have guessed that at the beginning, couldn't we? Don't you think? I mean, if I would have asked you to predict, you would have said the square, which is going to be a more efficient way of enclosing area, a square or a triangle.
People
Square.
don't square or triangle backwards.
True. But the most efficient then, and what you'd find is, if we did this, you hypothesize here, if we were to do this same problem for, let's say, a square and a pentagon, which one would win?
Pentagon.
The pentagon.
Circle. A circle is the ultimate.
Okay, circle would be the ultimate, yeah. If we were to take regular polygons, the more sides, what's happening to the angles as we get more sides?
They're more obtuse.
Yeah, they're getting more obtuse, right? And so the less, you could almost define this if you wanted to in terms of like a pointiness index. And you got to use the quotes there because that's pretty hokey. But if you wanted to think about the degree of angularity, the pointiness, if you wanted to define pointiness in terms of angles and numbers of, what you could find then is that the pointier an object is, the poorer it is at enclosing area, right? Now here's what's interesting about this, I think. If you take this problem, think about the three-dimensional equivalent. We could either take something like, if we were taking regular polyhedrons instead of, say, polygons.
Like a cube.
Here we'd have like a regular tetrahedron. Here we'd have a hexa, what do we call that? I don't know. It's a cube, right?
We just have a cube and a...
But as you start to get polyhedrons that have more faces and the angles start to grow, they start to look more what?
Round.
Well, not spherical, right?
Spherical.
So in the same way that the circle is the most efficient way of enclosing area, right? You get the most bang for your buck. You enclose the most area for the smallest perimeter, which we call circumference. Same thing is true for a sphere, right? If you went to 4 dimensions, a hypersphere. But we don't forget I said that.
Yeah, why do you say stuff?
Yeah, why do you say something you know we've never heard?
What is a hypersphere?
Yeah, okay. But now I want you to think about something. Think about animals now. Think about the physiology of animals
Okay.
based on where they live. Animals that tend to live, now for us,
Giraffes. They eat from tall trees.
no, giraffes are important. Hold that thought. Giraffes are part of that's something we got to consider.
Hippos. What about hippos?
We don't have to consider this because we lived in air-conditioned environments, and we're able to. We have intelligence that allows us to manipulate our environment to adapt. But most animals don't. For most animals, heat transfer is a real battle that they constantly fight. If you live in a really cold area, you want to preserve your heat, right? You don't want your heat to leak out because if you're a warm-blooded animal, your survival depends on maintaining a constant body temperature that's higher than the ambient temperature, right? So, well, right, exactly. So now think about animals, for example, that would live in the coldest possible climates.
Penguins.
Penguins would be a good example. And penguins would be a very good example, because not only do they live in the coldest climate, air is a really good insulator compared to water, right? So animals that live in cold water would be the absolute extremist of the extreme. Whales, penguins, walruses, etc.
They're more spherical.
They're more spherical, aren't they? They're more spherical. There's two things going on there. They're more spherical, so their pointiness is really low. They've got other adaptations too. They've got layers of blubber, and they store air in the fur and all that stuff. But if you look at the size, there's a definite huge evolutionary force at play there, telling that those guys, they can't be long and angular if they're warm-blooded, or they're going to die. Because they're going to have to expend so much energy staying warm that they won't be able to hunt and do things like that, right?
So you explain hippos because they're pretty red.
Okay, well, we'll get to that. Hippos are
The exception.
hippos. Now, first of all,
They also live in the water.
okay, but where do hippos live?
Water.
They live in the water. Okay, so they are able to regulate their temperature by being constantly in the water, which is not nearly as warm as the summer temperatures in their environment, right? Okay, now you might say, what about an elephant? Okay, but now think about an elephant. An elephant is cheating in a huge way. An elephant is adding a bunch of biological pointiness by having those enormous ears that have all that vasculature in the ear. Because they run a tremendous amount of blood through their ears. How come?
So they can hear.
Because it cools them down.
Yeah.
The main reason for elephants' ears is not hearing. They don't do a thing for hearing. It's the only part of the ear that really affects hearing is the part that acts like it's got to be concave in order to trap sound. So the elephant, the part that dangles way down there, doesn't do any. In fact, it probably hurts their hearing. It's not going to help it at all. But what it does is it cools their body.
They never forget.
And they never forget it. That's Now, the other thing that's going on there is if you look at the size of the creatures, what you find is that now think about this. Think about a sphere. Okay? As you increase the linear dimensions of a sphere, say the radius is the one linear dimension that describes the whole sphere. The surface area of the sphere it's 4 pi r squared, right? So every time you double the radius, you're quadrupling the surface area, right? But what about the volume? When you double the radius, the volume formula is 4/3 pi r cubed, right? So the volume, we'd say in math and physics, the volume goes as the cube of radius, whereas the surface area goes as the square of radius, right? Now think about that as you scale up and up and up. Let's say we take an object and we are going to increase its size by a factor of 10. If we increase the size by a factor of 10, then that means the surface is going to increase by a factor of 100. But the volume increases by a factor of 1,000. So the bigger the animal is, the more efficient it gets at keeping in its warmth. Because the warmth is stored, the warmth is generated, right? The metabolic parts of the animal are the inside parts, of course.
So little that is on the outside.
And you get the smallest amount on the outside, you get the smallest boundary to transfer that heat across, right? And so it makes sense then that whales are huge, that seals are huge. You know, the animals that are big tend to live in cold environments. Animals that are small tend to not. The very smallest animals in the world are little desert-dwelling rodents. I mean, those are a blind naked mole rat is very tiny, and it's got no hair, so but tree frogs are cold-blooded. But I mean, so right? You see the point? Yeah. Giraffes are they're an exception. Giraffes are a big animal that lives in warm climates, but are they very
sharp?
They're very sharp. They're very pointy, right? And you can see the veins running down a giraffe's. I mean, there's a lot of surface blood flow in a giraffe, and so yeah.
They're kind of short and acid.
Isn't that interesting, though? I think that's really interesting.
And then,
Oh.
you should throw that hat.